So this is problem 25.18, and it says we have two capacitors, C1 and C2, connected in series, shown here. And we have a 12-volt battery connected across them. Now the first thing we want to do is find the equivalent capacitance. We have a series, and we know that the equivalent capacitance is equal to 1 divided by C1 plus 1 divided by C2 to the power of -1. If we were to just plug in those numbers that are given to us, we get 12.0 microfarads. So if we were to redraw it, this is our situation here where we only have one capacitor with equivalent capacitance, 12 microfarads. Now B wants us to find the energy stored in this equivalent capacitance. We know the equation for that, U of E, for the equivalent capacitor is equal to 1/2 C equivalent delta V squared. We just plug in the numbers and we get 1/2 times 12 times 10 to the -6 farads times 12 volts squared. Plug in those numbers and you get 8.64 times 10 to the -4 joules. So we went from here, figured out what the equivalent capacitance was, and then we calculated how much electric potential energy is stored in this specific parallel plate. Now C wants us to find the energy stored in each individual capacitor. So here we have a certain amount of electric potential energy, and that's going to be divided up into this capacitor and this capacitor. Now something important when it comes to capacitors in series is that they carry the same charge. So Q1 is equal to Q2 is equal to, well, Q total. What I mean by that is that the electric charge on this capacitor is the same as the one on this capacitor, which is the same as the electric charge here. So they all have the same Q value. These two guys have different delta V's, but they have the same Q. Because we know that Q is equal to C equivalent delta V, which is equal to 144 microcoulombs. So we already knew what this was. We already know what this is because this is the voltage across the equivalent capacitor, right? So then we figured out, well, what's the charge? Same for all of them, and it's 144 microcoulombs. Then we can write out that the electric potential energy across one is equal to Q1 squared divided by 2C1 is equal to 1.44 times 10 to the -11 coulombs and all of that squared. And then we're going to have divided by 2 times, and then the capacitance is 18 times 10 to the -6 farads. And this is equal to 5.76 times 10 to the -4 joules. We do the same exact thing for E2, electric potential energy across capacitor number 2, Q2 squared, same charge, divided by C21, which is given to us. And then if you were to plug in the numbers, you get 2.88 times 10 to the -4 joules. Okay, so that was C. Now D says, show that the sum of these two energies is the same as the energy found in part B. So they're saying, okay, well, you know what the electric potential energy on this plate is. You know what it is on this plate. If you add them up, does it in fact give you the electric potential energy on this plate, which you also know? Pretty simple to show. We're going to just do 5.76 times 10 to the -4 joules plus 2.88 times 10 to the -4 joules. Add it all up and you get 8.64 times 10 to the -4 joules. And we see that it is in fact the same as what we got here. Now E asks us, is this always true? Or does it depend on how many capacitors there are? So is this a situation that's unique to there only being 2 capacitors, or does it matter how many capacitors? And the answer comes from conservation of energy. Right, so the idea is there's a certain amount of energy to the system, right? It doesn't matter that I represented it like this or like this. The capacitor here has the same amount of electric potential energy as the sum of these capacitors here. It doesn't matter if there's 3 or 4 of them, the sum of the electric potential energy on our capacitors is equal to the electric potential energy on the equivalent capacitor. So E says, is it always true? And we say, yes. Now F is asking us this question. It says, if the same capacitors were connected in parallel, what potential energy difference would be required across them so that the combination stores the same energy as in part A? Let's just draw this out. So here we have our capacitors connected in parallel, like this, so C1, C2, right? And we want to know, okay, what does delta V have to be across these two capacitors to give us a total electric potential energy 8.64 times 10 to the negative 4. And the reason why this is not the same as this is because the electric potential energy equation depends on the equivalent capacitance here. And the equivalent capacitance in series and parallel is not the same thing. Right, so here in parallel, C equivalent is just C1 plus C2. And we know that that's just going to be 54 microfarads. And we want to know, okay, well, we want to have the same electric potential energy in the equivalent situation. And what we know is that this is our equation, right? So we have a new C equivalent. So that means we necessarily need to change delta V for UE equivalent to be the same as it was before. So let's figure out what is delta V. And well, delta V is equal to, and then we just have, it's going to be the square root of 2 UE equivalent divided by C equivalent. So I'll just recap what we have here. We have this system now. It's a little bit different, the circuit, because these two are in parallel instead of in series. And we know that C equivalent is 54 microcoulombs or microfarad. And we want to figure out what does delta V have to be in this scenario here, right? We want to know what is delta V in this scenario here such that U equivalent is the same as it was before. So we want it to be 8.64 times 10 to the negative 4 joules. We plug in those numbers, so I'll just write them out. So 2 times 8.64 times 10 to the negative 4 joules divided by C equivalent, which is 54 times 10 to the negative 6 farads. And that's going to give us 5.66 volts. Okay, so essentially, what does the potential difference have to be across the equivalent capacitor? 5.66 volts. G then asks us to find which capacitor stores the most energy. So which one stores more energy, C1 or C2? Similar to the questions we've already have, we kind of want to figure out what is UE1 and what is UE2. So what is the electric potential energy across C1 and what is the electric potential energy across C2? Now we know what the equations are. U of E is equal to 1/2 C delta V squared. And the nice thing about capacitors in parallel is that they have the same delta V. So the potential difference across this one here is the same as is across C1 and C2. So here, delta V here is the same as delta V here, is the same as delta V here. The difference, however, is that this capacitor does not carry the same amount of charge as this capacitor, which is not necessarily the same amount of charge as this one here, right? But for the sake of this problem, we know what C is, so UE1 is equal to 1/2 C1, and they have the same value delta V, so we know what delta V is. UE2 is going to be equal to 1/2 C2 delta V squared, with the same delta V. So we know that whichever one is bigger, so C1 or C2, will have the largest electric potential energy. We can just remind ourselves, C2, right, is obviously a lot bigger than C1. So if C2 is bigger than C1, C2 is going to store more electric potential energy. And that is it.